Now here the question is, we are given this function and it says, if fx is continuous at x equals 2, find the value of a and find the value of f2. Now what we'll do is, first we'll write its left-hand limit. Now left-hand limit will be limit x tends to 2 negative, and when x is less than 2, this is the definition. So this is e to the power x plus 2 log 4 whole to the power greatest integer function of x plus 1 divided by 4 minus 16 upon 4 to the power x minus 16. Now what we'll do is, we'll take this x plus 2 to the power of 4 and then e and log will cancel. So we can write this as limit x tends to 2 negative, and it will be e to the power log 4 to the power x plus 2 and whole to the power this greatest integer function of x plus 1 upon 4 minus 16 upon 4 to the power x minus 16. Now this e and log will cancel, and we also know that when x tends to 2 negative, greatest integer function of x, it is 1, as x is less than 2, and greater function of x, it doesn't take a limiting value, so we have to put the value of greater function of x. So now it will be this limit x tends to 2 negative 4 to the power of x plus 2 to the power of, now this is 1 plus 1, 2 upon 4 is 1 by 2 minus 16 upon 4 to the power x minus 16, which we can also write as limit x tends to 2 negative 4 to the power x plus 2 upon 2 minus 16 upon 4 to the power x minus 16. Now we'll solve this limit. Now first we'll check its form. If we put x is 2 negative, now this is 4 square 16, 16 minus 16 is 0, and this again is 4 square 16, 16 minus 16 is 0, so this is the 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So we can write this as limit x tends to 2 negative, and then this is 4 to the power x plus 2 by 2 log 4, and derivative of x by 2 is 1 by 2. And in the denominator will be 4 to the power x log 4. Now this log 4 will cancel. Now if we put x as 2, this is 4 square, which is 16 into 1 by 2, and here also it is 16. So value of this left hand limit is 1 by 2. Now we'll find its right hand limit. Now its right hand limit will be limit x tends to 2 positive. Now when x is greater than 2, this value is a into 1 minus cos x minus 2 upon x minus 2 10 x minus 2, which again is 0 upon 0 form. Now what we'll do is, we'll multiply and divide this denominator with x minus 2. Now this is standard limit 10x upon x, which is 1, and this is 1 plus cos x upon x square, and it is 1 by 2. So this right hand limit will be 1 by 2. Now since this function is continuous at x equal to 2, then left hand limit, which is 1 by 2, must be equal to its right hand limit, and it must be equal to its function value at 2. So here value of a is 1 and value of f2 must be 1 by 2. Now here the question is, we are given this function fx, which is x plus 2 when x lies between minus 4 and 0. There is 2 minus x square when x lies between 0 and 4. We need to find f of fx, domain of f of fx, and also we need to comment upon the continuity of f of fx. Now since this is f of fx, first we'll draw the graph of fx. So we have these x's. When x is minus 4, this value is minus 2. And when x is 0, this value is plus 2. So this is minus 2 and this is plus 2. And here when x is 0, this is 2. And When x is 4, this is minus 14. So at 4, this is suppose minus 14, not to be scaled. So here this definition is x plus 2, and here this definition is 2 minus x square, and there is a definition change at this point 0, and the boundary points are minus 4 and plus 4. Now we'll draw horizontal lines at minus 4, 0 and 4. So we'll draw a horizontal line at minus 4, a horizontal line at 0 and a horizontal line at plus 4. And we'll mark these point of intersections. So we have this point, we also have this point, and then we have this point. Now we'll find these points. Now if x plus 2 equals 0, this point is minus 2. If 2 minus x square, it is equal to 0, then this point is root 2. And here this point is intersection of this graph, which is 2 minus x square with this line, which is minus 4. So this point is actually root 6. Now in between minus 4 and 0, definition is x plus 2. So here this definition is x plus 2, and in between 0 and 4, this definition is 2 minus x square. So now we'll start writing f of fx. So we have f of fx. Now first interval is between minus 4 and minus 2. So when x lies between minus 4 and minus 2, now since this function is continuous, again we need not bother about this equality sign. So here this definition is x plus 2, and this definition, it lies within these two lines. So this x plus 2 will go to x plus 2. So here it will be this x plus 2 plus 2. Now this next interval is between minus 2 and 0. So when x lies between minus 2 and 0, again this definition is x plus 2. Now it will go to this 2 minus x square. So it will be this 2 minus x plus 2 whole square. Now the next one is from 0 to root 2. So when x lies between 0 to root 2, definition here is 2 minus x square, and we'll go to this definition. So it will be this 2 minus x whole square. Now this next interval is between root 2 and root 6. So when x lies between root 2 and root 6, here this definition is again 2 minus x square. Now I'll go to this x plus 2. So it will be 2 minus x square plus 2. Now when x lies between root 6 and 4, we have this definition which is 2 minus x square, but then here definition of fx does not exist. So this is the only definition possible for f of fx. So we can write this as x plus 4 when x lies between minus 4 and minus 2, and this 2 minus x plus 2 square when x lies between minus 2 and 0. This is 2 minus x whole square when x lies between 0 and root 2, and then it will be this 4 minus x square when x lies between root 2 and root 6. Now this function is defined from minus 4 to root 6. So domain of f of fx will be from minus 4 to root 6. Now since fx is continuous, its composition with itself will also be a continuous function. So this function will be continuous in its domain, which is from minus 4 to root 6. So this is our graphical method. Now we'll solve this question using algebraic method. Now for algebraic method, we have this fx, which is defined as x plus 2 when x lies between minus 4 and 0, and it is 2 minus x square when x lies between 0 and 4. Now we need to find f of fx. Now f of fx is fx plus 2 when fx lies between minus 4 and 0, and it will be 2 minus fx square when fx is greater than 0 but less than 4. Now we have two definitions of fx. So we'll split this definition in 4 parts. So now we want to write this definition. Now first we'll take this x plus 2. So we'll put fx as x plus 2 in these two. So it will be x plus 2 when x plus 2 lies between minus 4 and 0, and this condition, which is when x lies between minus 4 and 0. And the next one is 2 minus x plus 2 square when x plus 2 lies between 0 and 4, and again it is true when x lies between minus 4 and 0. Now we have this other definition, which is 2 minus x square. So it will be this 2 minus x square plus 2 when minus 4 is less than or equal to 2 minus x square is less than or equal to 0, and here value of x lies between 0 and 4, and then we have 2 minus x square whole square when 0 is less than 2 minus x square is less than 4, and x lies between 0 and 4. Now first we'll simplify these intervals. Now here the value of x is minus 6 is less than x is less than minus 2, and here it is from minus 4 to 0. Now if we take intersection of these two conditions, we'll get the value of x between minus 4 and minus 2. So first definition is from minus 4 to minus 2, and it will be this x plus 4. Now for the second one, it will be this minus 2 and then x and then 2, and here it is from minus 4 to 0. So here common between the two is from minus 2 to 0. So next one is from minus 2 to 0, and here this definition is 2 minus x plus 2 whole square. Now in this, if we solve this, we can write this as minus 6 is less than or equal to minus x square is less than or equal to minus 2, or if we multiply with minus and take square root, it will be this x will lie between root 2 and root 6, which lies in this interval. So here this condition is the value of x should lie between root 2 and root 6. Now in this interval, value of fx is 4 minus x square. And finally, we have this, which is minus 2 is less than minus x square is less than 2. So here we'll have mod of x is less than root 2. So this is from 0 to root 2. So when x lies between 0 and root 2, this definition will be 2 minus x square whole square. Now again, it goes from minus 4 to minus 2, minus 2 to 0, 0 to root 2, and root 2 to root 6. So for this, f of fx domain is from minus 4 to root 6. Now if we look at continuity, we'll check continuity at minus 2. So f minus 2 negative, it will be 4 minus 2, 2, and then f minus 2 positive, and since equality sign is here, so this is also equal to f2, and f2 positive will be 2 minus 0. This is 2, so it is continuous at minus 2. Now we'll check continuity at 0. f0 negative is also equal to f0, and here if we put x as 0, it will be 2 minus 4. So it will be this minus 2, and f0 positive, it will be 2 minus 4, which again is minus 2. So it is continuous at 0 also. Now we'll check its continuity at root 2. Now f of root 2 negative, now this is 0, 2, and f of root 2 will be equal to f of root 2 positive, and here it will be 4 minus 2 and it is 2. So this function is continuous in its domain. So we can find f of fx using graphical method as well as using algebraic method. Now here the question is, we are given that gx equals this limit n tends to infinite x to the power n fx plus hx plus 1 divided by 2x to the power n plus 3x plus 3, and x is unequal to 1. And it also says g1 is this limit x tends to 1 sine square pi into 2 to the power x upon log secant pi into 2 to the power x. Now it says, if it is a continuous function at x equals 1, then find the value of 4g1 plus 2f1 minus h1, assuming fx and hx are continuous at h equals 1. Now what we'll do is, we'll first solve this limit, which is g1. Now if we put x as 1, this is sine 2 pi, and sine 2 pi is 0, and here will be the secant 2 pi, which is 1, and log 1 is 0. So this is 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So it will be this limit x tends to 1, and we can write this as 2 sine pi into 2 to the power x into cos pi into 2 to the power x, and then it will be this pi 2 to the power x log 2, and here in the denominator will be 1 upon secant pi 2 to the power x, and then secant x is secant x tan x pi 2 to the power x, and 10 pi 2 to the power x, and then it will be pi 2 to the power x log 2. Now secant function will cancel, this pi 2 to the power x log x will cancel. Now here sine and sine will also cancel, so it will be this limit x tends to 1 2 cos square pi into 2 to the power x. Now if we put x as 1, this is cos 2 pi, and cos 2 pi is 1. So answer to g1 is 2. So we have value of g1, and value of g1 is 2. Now we'll calculate left hand limit and right hand limit at x equals 1. Now if we write its left hand limit will be limit x tends to 1 negative gx, which is limit x tends to 1 negative, and it will be this limit n tends to infinite x to the power n fx plus hx plus 1 upon 2x to the power n plus 3x plus 3. Now we know that as x tends to 1 negative, that is x is little less than 1, then as n tends to infinite x to the power n, it approaches 0. So this expression will be 0, and this expression also will be 0. So we can write this as limit x tends to 1 negative hx plus 1 upon 3x plus 3. Now we put this limit, this is h1 negative, and in the question it is given that fx and gx are continuous functions. So this is h1 plus 1 upon 6. So our left hand limit is G1 negative, and it will be H1 plus 1 by 6. Now we'll find our right hand limit. Now this right hand limit is limit x tends to 1 positive gx, and it will be this limit x tends to 1 positive, and then limit n tends to infinite x to the power n fx plus hx plus 1 upon 2x to the power n plus 3x plus 3. Now when x approaches 1 positive, that means x is greater than 1. And if x is greater than 1, then as n approaches infinite, x to the power n also approaches infinite. So what we'll do is, we'll divide everything with x to the power n. And if we divide everything with x to the power n, we'll have hx plus 1 upon x to the power n and 3x plus 3 upon x to the power n. So it will be this limit x tends to 1 positive, limit n tends to infinite fx plus hx plus 1 upon x to the power n divided by 2 plus 3x plus 3 upon x to the power n. Now as n tends to infinite, this expression will be 0 and it will also be 0. So this right hand limit will be this limit x tends to 1 positive fx by 2, which is f1 by 2 as fx is continuous. So the right hand limit of this function will be f1 by 2. Now once we have function value, left hand limit and right hand limit, then for condition of continuity, we know that all the three, they must be equal. So if we equate them, then we can write 2 equals h1 plus 1 by 6, and it is equal to f1 by 2. So from here we'll get h1 is 11 and f1 is 4. So now we have the value of g1, h1 and f1. Now we need to find the value of 4g1 plus 2f1 minus h1. Now 4g1 is 2, f1 is 4 and minus h1 is 11. Now this is 16, 16 minus 11 is 5. So answer to this question is 5. Now here the question is, we are given this function fx and it says if f is continuous at x equal to 0, then find the value of a. Now if we find its right hand limit, then the right hand limit at 0 will be f0 positive, and we can write this as limit x tends to 0 positive, and when x is greater than 0, that's the definition, a to the power sin x minus a to the power 10x upon 10x minus sin x. What we'll do is, we'll take minus a to the power sin x common. So if we take minus a to the power sin x common, then we can write this as limit x tends to 0 positive minus a to the power sin x, then it will be a to the power 10x minus sin x minus 1 upon 10x minus sin x. Now this is a to the power 0, which is 1, and this is a to the power x minus 1 upon x when x tends to 0, as 10x minus sin x is 0. So this is standard limit ln a, and this is 1. So value of this limit will be minus ln a. So for this function, right hand limit is minus ln a. Now we will find its left hand limit. Now left hand limit is f0 negative, and will be this limit x tends to 0 negative, and this is log 1 plus x square plus log 1 minus x plus x square upon secant x minus cos x. Now this is log m plus log n. So it will be log m into n, and this is a plus b into a minus b. So it will be a square minus b square. So I'll directly write this as limit x tends to 0 negative, and this is log m into n. Now this is a plus b, a minus b. So it will be 1 plus x square whole square minus x square, and we let this secant x as 1 upon cos x. So it will be 1 minus cos square x, which is sin square x into cos x. Now we simplify this, we can write this as limit x tends to 0 negative, and here it will be log 1 plus x to the power 4 plus x square upon sin square x, and cos 0 is 1. Now log 1 is 0, sin 0 is 0, so it is 0 upon 0 form. And if it is 0 upon 0 form, we'll use L'Hopital's rule. So we'll write this as limit x tends to 0 negative. I'll be 1 upon 1 plus x to the power 4 plus x square into its derivative, which is 4x cubed plus 2x, and here it will be this 2 sin x into cos x. Now what we'll do is we'll multiply and divide everything with x. Now sin x upon x, it is 1, and here if we cancel this x, we'll get this as 4x square plus 2. Now we'll put the value of x as 0. Now this is 1, and here it will be 2 upon 2, and cos 0 is 1. So this left hand limit is 1. So once we have left hand limit and right hand limit, we can find the value of a. Now right hand limit is minus log a. So if we equate them, we'll get minus log a equals 1, or log a equals minus 1, that is a equals 1 upon e. So here the value of a is 1 by e. Now from here the story of gx begins. Now it says gx is log 2 minus x upon a into cot x minus a for x unequal to a unequal to 0, and a greater than 0. And it says if gx is continuous at x equals a, then show that g e to the power minus 1 is equal to minus e. Now basically a in this case is 1 upon e. So we can write this gx as log 2 minus ex into cot x minus 1 upon e when x is unequal to 1 upon e. Now if it is continuous at 1 upon e, then g1 upon e must be equal to this limit x tends to 1 upon e gx, and this gx is log 2 minus ex upon 10 x minus 1 upon e. Now we put x as 1 upon e, this is log 1, which is 0, and here it is 10 0, so it is 0 upon 0 form. So again we'll use L'Hopital's rule. So it will be this limit x tends to 1 upon e, and here will be this 1 upon 2 minus ex into minus e, and this will be secant square x minus 1 upon e. Now we put x as 1 upon e, 2 minus 1 will be 1, so it will be this minus e, and here secant square 0 is 1. So from here we can say value of g1 upon e is minus e, which is what we need to prove in this question. Now here the question is, let fx plus y is equal to fx plus fy for all xy. And it says if fx is continuous at x equals 0, then show that fx is continuous at all x, and that's our first question. Now if we put x and y both 0, then we'll get f0 equals f0 plus f0. That means a value of f0 must be 0. So for this function, f0 is 0. Now it says fx is continuous at 0. And if fx is continuous at 0, that means f0 minus h must be equal to f0 plus h, and it will be equal to f0, and f0 in this case is 0. Now we need to show that it is continuous for all x. Now if we take any x belongs to R, then left hand limit at any x will be f x minus h. Now it is given that fx plus y is fx plus fy. So we can write this as fx plus f minus h. Now f minus h is f0, which is 0. So it will be equal to fx. And if we look at its right hand limit, which is fx plus h. Now fx plus h is fx plus fh. Again this fh is 0. So this is also equal to fx. So for any real x, fx minus h will be equal to fx plus h, and it is equal to fx. That means this function is continuous for all x belongs to R. Now we'll solve this second question, which is if fx into y is fx into fy for all xy and fx is continuous at 1, then prove that fx is continuous for all x except x equals to 0, and we are given that f1 is unequal to 0. Now it says fx is continuous at x equals 1. Now that means f1 minus h will be equal to f1 plus h, and they'll be equal to f1, and none of it is equal to 0. Now if we look at any point A which is R except 0, then we can write left hand limit as limit h tends to 0 f a minus h. Now it will be this limit h tends to 0. Now we can write this as f, and if we take a common, it will be a into 1 minus h upon a. Now fx into y is fx into fy. So we'll write this as limit h tends to 0 fa into f1 minus h upon a. Now f1 minus h upon a is f1 negative, which is f1 minus h, and it will be equal to f1. So this is fa into f1. And the same way we want to write its right hand limit. Now right hand limit will be limit h tends to 0, and then it will be this f a plus h, which is this limit h tends to 0 f a into 1 plus h upon a, which again is fx into fy. So it is limit h tends to 0 f a into f1 plus h by a. Now this is f1 plus h, which is right hand limit at 1, which again is f1. So this is fa into f1. Now if we look at this function again, we are given that fxy equals fx into fy. Now if we put both x as 1 and y as 1, we can write f1 equals f1 square, which is the quadratic in f1. So from here we'll get this condition that either f1 is 0 or f1 is 1. Now f1 is unequal to 0, it is given in the question. So the only condition that we have here is value of f1 is 1. Now if we put f1 is 1, then this is fa and this is also fa. So for all the points a which are r minus 0, fa negative is equal to fa positive, and will be equal to fa. That means this function is continuous for all such a's. Now what will happen at a equals 0? Now at a equals 0, if we look at its left hand limit, its left hand limit will be limit h tends to 0 f minus h, which is f minus 1 into f0, and this f minus 1 may not be equal to 1. So at a equals 0, it may be continuous and it may be discontinuous. So it is not necessarily true. So this function is continuous for all x except at 0. And one counter example can be if we take this function fx as 1 upon x when x is equal to 0 and 0 at x equal to 0. Now this function, it satisfies all the conditions and it is continuous for all x belongs to r minus 0, and at 0 this function is discontinuous. Now here we are given this function fx, which is this summation r varies from 1 to n 10 x upon 2 to the power r into secant x upon 2 to the power of r minus 1 for all Rn belongs to n. What we'll do is first we'll simplify this. Now if we let x upon 2 to the power r as theta, then x upon 2 to the power r minus 1 will be 2 theta. So first we'll simplify this, which is 10 theta into secant 2 theta, and what we'll do is we'll write this as sin theta upon cos theta into cos 2 theta. Now we're going to write this sin theta as sin 2 theta minus theta upon cos theta cos 2 theta. This is sin a minus b, which is sin a cos b minus cos a sin b upon cos theta cos 2 theta. Now if we split this, we can write this as this is 10 to theta minus 10 theta. So we can write this function fx as this summation r varies from 1 to n and 10 theta into secant 2 theta is 10 to theta minus 10 theta. So it will be this 10 x upon 2 to the power of r minus 1 minus x upon 2 to the power of r. Now if we put values of r, we'll get this as 10x minus 10x by 2 plus 10x by 2 minus 10x by 2 square, and will continue up to 10x upon 2 to the power of n minus 1 minus 10x upon 2 to the power of n. Now all these terms, they'll cancel. So in the end, we'll have this fx as (10x minus 10x upon 2 to the power n). Now we can also write fx plus 10x upon 2 to the power n as 10x. So this is our first result. Now we are given this function gx, which is defined as limit n tends to infinite, and will be this log fx plus 10x upon 2 to the power n minus fx plus 10x upon 2 to the power n whole to the power n into greatest in the function of sin 10x by 2 whole divided by 1 minus fx plus 10 x upon 2 to the power n whole to the power n. Now we know that fx plus 10 x upon 2 to the power n is nothing but 10x. So it will be this limit n tends to infinite log 10x minus 10x to the power n into sin 10x by 2 greatest real function upon 1 minus 10x to the power n. When x is unequal to pi by 4 and gx is equal to k at pi by 4, that means f pi by 4 it is equal to k. Now it says find the value of k if fx is continuous at pi by 4. If we look at x tends to pi by 4, then x by 2 is pi by 8, then this 10 x by 2 will be nearly root 2 minus 1, and sine of root 2 minus 1, it is not equal to 1, it will be less than 1. And if it is less than 1, then this greatest unit function of sine 10x by 2 will be 0. So value of this greatest unit function of x will be 0 when x approaches pi by 4. So we'll write this as gx equals limit x tends to pi by 4, limit n tends to infinite, log 10x upon 1 minus 10 x to the power n. Now if we consider its limit at pi by 4 negative, it will be this limit x tends to pi by 4 negative, it will be this limit n tends to infinite log 10x upon 1 minus 10 x to the power n. Now when x is less than pi by 4, then 10x is less than 1, and if 10x is less than 1, then 10x to the power n will be 0 as n approaches infinite. So it will be this limit x tends to pi by 4 negative, and this is log 10 pi by 4, and which is log 1, that is 0. So left hand limit at pi by 4, it is 0, and if we look at right hand limit at pi by 4, right hand limit will be g pi by 4 positive, and it will be this limit x tends to pi by 4 positive, limit n tends to infinite log 10x upon 1 minus 10 x to the power n. Now when x approaches pi by 4 positive, 10x is greater than 1, and in that case 10x to the power n will approach infinite, and anything finite upon infinite is 0. So in this case this function will actually be 0. So if gx is continuous at pi by 4, then in that case left limit must be equal to right limit, and it must be equal to value at pi by 4. We'll get the value of k as 0. So for this question, value of k is 0. Now it says also state points of discontinuity of gx in the interval 0 to pi by 4. Now in 0 to pi by 4, we know that gx is this limit n tends to infinite log 10x minus 10x to the power n, greatest unit function of sine 10x by 2 upon 1 plus 10x to the power n. Now in this interval 10x to the power n will be 0 as n tends to infinite. So this is 0 and this is 0. So in this interval gx is simply log 10x, and since 10x is continuous in 0 to pi by 4 and log x is continuous when x is greater than 0, this log of 10x, it is continuous in x belongs to 0 to pi by 4, and there will be no point of discontinuity of gx in this interval. Now here the question is, we are given this function fx which is x cube minus x square minus 3x minus 1, and we are given hx as fx upon gx. What we'll do is we'll write this as x cube minus x square minus 2x minus x minus 1, and if we take x common, it will be x into x square minus x minus 2, and then minus x plus 1 which is x, and this is x plus 1 into x minus 2 minus x plus 1 which will be x plus 1 x square minus 2x minus 1. So that's our fx. Now it says this hx is continuous everywhere except when x is equal to minus 1. Now if it is continuous everywhere except at minus 1, that means this gx, it must contain one of the vector x plus 1, and then there will be some function hx which has no real root. Only then this function will be continuous everywhere except at x equals minus 1. Now it says limit x tends to infinite, hx is infinite. In part B it says limit x tends to infinite, fx upon gx, it is infinity. Though it is not given the question, but then gx, it has to be a polynomial function for this question. So I'll assume this gx, it is a polynomial function. Now if this limit is infinite, that means degree of fx, it must be strictly greater than degree of gx. Now degree of fx is 3, so degree of gx will be less than 3. Now we already know there is this one factor x plus 1, so degree of gx, it can be either 1 or 2. Now in C it says this limit x tends to minus 1, hx, it is 1 by 2. That means this limit x tends to minus 1, x plus 1, x square minus 2x minus 1 upon a, x plus 1 hx, this value will be 1 by 2. Now this x plus 1 will cancel. Now from here we can say this degree of gx, it cannot be 2, because if it is 2, then in that case it will be a quadratic equation, and this quadratic equation will have two roots, alpha and beta. Now one of the root is minus 1. Now if we get second root which is not minus 1, then this function will be discontinuous at 2 points, minus 1 and beta. If we take this beta as minus 1, then in that case this limit, it won't be finite, it will be this infinite limit. So that means degree of gx can only be 1. So if degree of gx is 1, there is no hx in this expression. So from here we can say this limit x tends to minus 1, x square minus 2x minus 1 upon a, it must be equal to 1 by 2. Now if we put x as minus 1, it will be this 2 upon a equals 1 by 2. Value of a must be 4. So from here we get value of a as 4. And if a is 4, then this gx will be 4 x plus 1. So now we have gx, fx is already given, fx is x plus 1, x square minus 2x minus 1, and fx upon gx is hx. So this hx will be x square minus 2x minus 1 by 4. Now it says find the value of this limit x tends to 0, 3hx plus fx minus 2gx. So it will be equal to this 3h0 plus f0 minus 2g0. Now h0 is minus 1 by 4, so it will be this minus 3 by 4. Now f0 is minus 1 and then minus 2, and g0 is 4, so it will be this 9, 36. 36 minus 3 is minus 39 by 4. So value of this limit is minus 39 by 4. Now here the question is, we are given this function f which is continuous on the interval 0 to 1, and it is given that f0 equals f1. Then prove that there exists a point C in 0 to 1 by 2 such that fc equals fc plus 1 by 2. Now what we'll do is, we'll let a function say gx which is f x plus 1 by 2 minus fx. Now since f is continuous, fx plus 1 by 2 minus fx will be a continuous function. So from here we can say this gx is a continuous function. Now if we find the value of g0, then the value of g0 will be f1 by 2 minus f0, and say this value is k. And if we find the value of g1 by 2, value of g1 by 2 will be f1 minus f1 by 2. Then the question it says f1 is equal to f0. So it will be this minus f1 by 2 minus f0, which is minus k. Now we multiply them, we can write g0 into g1 by 2 will be equal to minus k square, which is less than or equal to 0. Then from Bolzano's theorem we can say that there exists at least one c in the interval 0 to 1 by 2 such that gc equals 0. Now if we put gc equals 0, we get f c plus 1 by 2 minus fc equals 0 or fc equals fc plus 1 by 2. So we have solved this question using Bolzano's theorem. We can also solve this question using intermediate value theorem. Now here the questions, we are given this function fx which is defined as this limit n tends to infinite cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n, which we will take common, and it will be this x minus 1. Now if we find the value of f1, if x is 1, then x to the power 2n will be 1. So in that case this value will be cos pi minus, now this is 1 and this is sin 0. Sin 0 is 0, and here will be this 1 plus 0. So value at x equals to 1 is minus 1. Now if we look at its left hand limit, so it will be this f1 negative, which is limit x tends to 1 negative, limit n tends to infinite cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n into x minus 1. Now x tends to 1 negative means value of x is less than 1, and if x is less than 1, then x to the power n is 0 as n tends to infinite. So in this case it will be this limit x tends to 1 negative, and it will be this cos pi x, x to the power n part will be 0 upon 1, and value of cos pi is minus 1. So for this function, left hand limit is minus 1. Now we will find its right hand limit. Now right hand limit will be f1 positive, and will be this limit x tends to 1 positive, limit n tends to infinite. Now this is cos pi x minus x to the power 2n sin x minus 1 upon 1 plus x to the power 2n into x minus 1. Now here x is greater than 1, and if x is greater than 1, then x to the power infinite is infinite. So what we'll do in this case is we'll divide everything with x to the power 2n. So if we put this limit, then we'll get this as limit x tends to 1 positive. Now cos pi x upon x to the power 2n will be 0. So here we'll get minus sin x minus 1, and here also 1 upon x to the power 2n will be 0. We'll get x minus 1. Now this is 0 upon 0 form, which is standard sin x upon x limit. So its value is minus 1. So for this function, left hand limit, it is equal to its right hand limit, and it is equal to its function value. So this function is continuous at x equals 1. And that's your option D. Now here the question is, we are given this function f which is continuous in R, and it says f 1 upon 4 to the power n, it is equal to sin e to the power n into e to the power minus n square plus n square upon n square plus 1. We need to find the value of f0. Now we know that as n approaches infinite, 4 to the power n approaches infinite, and 1 upon 4 to the power n, it approaches 0. So what we'll do is we'll take this limit n tends to infinite both sides. So this is n tends to infinite f 1 upon 4 to the power n, and this is limit n tends to infinite sin e to the power n into e to the power minus n square plus this limit n tends to infinite n square upon n square plus 1. And the question says fx is a continuous function, and if it is continuous, then we can take this limit inside this function f. If this information was missing from the question, fx is continuous, we could not take this limit inside this function. Now since f is continuous, we'll take this limit inside, and we know that as n tends to infinite, 1 upon 4n tends to 0. So this is f0. Now here in this case, it will be this limit n tends to infinite. Now sin e to the power infinite is sin infinite, and sin infinite is oscillating value from minus 1 to plus 1, and this is e to the power minus infinite, and which is 0. Now 0 into anything finite is 0, plus in this case it is an infinite limit. Highest power of n in the numerator and denominator is 2. So answer to this limit is coefficient of n square in the numerator upon coefficient of n square in the denominator. So from here we can say value of f0, it must be equal to 1, and that's your option B. In this question, value of f0 is 1, and also there is this one option that data is sufficient to find f0. So correct options are B and C. Now here the question is, we are given this function fx which is signum of cos 2x minus 2 sin x plus 3, and we need to find which of the following is true. Now for signum function, we know that if we have any signum gx, then this signum gx will be 1 when gx is greater than 0, 0 at gx equals 0, and will be minus 1 where gx it is less than 0. Now what we'll do is we'll find a range for this function. So we look at cos 2x minus 2 sin x plus 3 when x belongs to 0 to 2 pi. Now since this function is periodic with period 2 pi, we'll work out the solution in 1 period. The range of this function, it will be, that means this expression is either greater than 0 or it is equal to 0. Now we know that whenever gx is greater than 0, it will be 1, and at 0 it is 0. So what we'll do is we'll find the points where this function is 0. So this is 4 minus 2 sin square x minus 2 sin x equals 0, or we can write this as sin square x plus sin x minus 2 equals 0. Now we factorize this, we can write this as sin x plus 2 into sin x minus 1 equals 0. That is, the value of sin x is 1. It is possible if x is pi by 2. So that means this cos 2x minus 2 sin x plus 3, it is 0 when x is pi by 2, and it is greater than 0 if x lies between 0 to 2 pi except pi by 2. Now we'll talk about this signum function. So this function fx will be 0 at x equals pi by 2, and it will be 1 when x is not equal to pi by 2. Now if we draw graph of this function fx, will be this 0 and then pi by 2, and this is 2 pi. Now this value will be 1 except at pi by 2 this value is 0. And since it is a periodic function, this graph will be repeated like this. Now whenever this function will have a discontinuity, it will have discontinuity at odd multiple of pi by 2. It will be discontinuous at 2n plus 1 pi by 2, and it is an isolated point discontinuity, and that's your option C. Now here the question is, we are given two functions gx and fx, and then they have defined this function hx, which is mod of gfx. Now we need to find whether h is continuous or discontinuous at x equals 0. Now first we'll find its left hand limit. Now left hand limit will be limit x tends to 0 negative. So it will be this limit x tends to 0 negative mod of gfx. So value of x 0 negative will go into fx. Now if you look at this fx is greatest integral function of x upon greatest integral function of x plus 1, which we can also write as greatest integral function of x upon greatest integral function of x plus 1. Now if we put x as 0 negative, then in the denominator we'll have minus 1 plus 1, and there will be 0. So for this function fx, domain is defined from 0 to infinite union minus infinite to minus 1. So in the left neighborhood of 0, this function fx, it doesn't exist. That means this function g of fx will also not exist. So for this function hx, this left hand limit, it is not possible. Now if we look at its right hand limit, it will be h tends to 0 positive, and then it will be this limit x tends to 0 positive g fx. Now if x approaches 0 positive, then greatest integral function of x will be simply 0. So in this case, f0 positive will be exactly 0. We also have this fractional part x function here, but it won't make any difference. Now we are going to put value of f in this function g. So it will be this mod of tan inverse 0 minus cot inverse 0. Now tan inverse 0 is 0 and cot inverse 0 is pi by 2, and mod of minus pi by 2 is plus pi by 2. So right hand limit of this function is pi by 2. Now we'll find value of this function at 0. Now h0 is g of f0. Now f0 is clearly 0, so it will be this g0, and g0 is again tan inverse 0 minus cot inverse 0, which is pi by 2. So for this function gx, h0 equals h0 positive, and on the left hand side this function is not defined. So this function is continuous at x equal to 0. So the fundamental here is, if function is not defined on one side, then for continuity we want to check either fa and fa positive, and if it is not defined on the right, then for continuity fa should be equal to fa negative. So answer to this question is this option A. Now here the question is, we are given this function fx, which is limit n tends to infinite x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n when x is greater than 0 and x is unequal to 1, and value of this function at x equals to 1 is 0. Now we need to find its continuity at x equals 1. Now if we look at its left hand limit f1 negative, then will be this limit n tends to infinite. Now this is x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n when x tends to 1 negative. Now x tends to 1 negative means x is less than 1, and if x is less than 1, then as n approaches infinite, x to the power n, it approaches 0. So what we'll do is we'll write this as limit n tends to infinite when limit x tends to 1 negative 1 minus, now this is sine x to the power n upon x to the power n, and this is 1 plus sine x to the power n upon x to the power n. Now this is 0 upon 0 form, which is standard limit, so it will be 1 minus 1 upon 1 plus 1, and which is 0. So left hand limit for this function is 0. Now we'll find its right hand limit. Now for f1 positive, we can write this as limit n tends to infinite x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n. Now when x is 1 positive, so this limit is x tends to 1 positive. X is greater than 1, that means x to the power n approaches infinite as n approaches infinite. So this is infinity upon infinity form. So what we'll do is we'll divide everything with x to the power n. So it will be this limit x tends to 1 positive, limit n tends to infinite 1 minus sine x to the power n upon x to the power n, and this is 1 plus sine x to the power n upon x to the power n. Now this is not standard limit because sine x to the power n is not 0 but sine infinite, and sine infinite is oscillating value between minus 1 and plus 1 divided by infinite, and finite upon infinite is 0. So this value will be 0 and this value will be 0. So value of its right hand limit is 1. So that means f1 is equal to f1 negative, but it is not equal to f1 positive. So this function is left continuous, but it is discontinuous, and since left hand limit is not equal to right limit, it is a non-removable discontinuity, which in this case is a finite discontinuity at x equals 1. That's your option B. Now we are given this function fx when x is unequal to 0 and 0 for x equals 0. Now we need to find continuity of this function at x equals 0. Now it is given that f0 is equal to 0. What we'll do is we'll first find its left hand limit. Now left hand limit will be f0 negative, and will be this limit x tends to 0 negative, and then greatest linear function of fractional part of mod x into e to the power x square, fractional part of greatest linear function of x plus fractional part of x upon e to the power of 1 upon x square minus 1 into sigma sin x. Now we know that greatest integer function of fractional part is always 0. In the same way, fractional part of greater function will also be 0, and this is e to the power 0, which is 1. Now if we look at this denominator, then here in this case it will be e to the power infinite minus 1, which is infinite, and here signum of sine x. Now when x is less than 0, sin x is negative. In this case, signum of sin x will be simply minus 1. So this is 0 upon infinite, and 0 upon infinite is 0. So left hand limit for this function is 0. Now if we find its right hand limit is f 0 positive, and it will be this limit x tends to 0 positive, and again it will be this greatest limit function of fractional part of mod x e to the power x square, fractional part of greatest limit function of x plus fractional part of x upon e to the power 1 upon x square minus 1 into signum of sin x. Now again this is 0, and this is 1. This again is infinite, and when x is positive, sin x is positive, so this is plus 1. So again it will be 0. So for this function, f0 is equal to f0 negative, and it will be equal to f0 positive. So this function is continuous at x equals to 0. Now here we are given this function fx, and it says we need to check continuity of fx at x equals 0. Now if we find left hand limit at 0, it will be this limit x tends to 0 negative x into greatest function of x square log 2 base 1 plus x. Now we know that greatest function of x, it doesn't take a limiting value, it takes exact value. Now when x is 0 negative, then greater function of 0 negative is minus 1, and minus 1 square will be plus 1. So we can write this as limit x tends to 0 negative x, here this value is 1, and we can write log a upon b as ln a upon ln b. So it will be this log 2 upon log 1 plus x. Now this is standard limit 1, so its left hand limit is log 2. Now we'll find its right hand limit. Now f0 positive will be this limit x tends to 0 positive log e to the power x square plus 2 times under root of fractional part of x upon 10 under root x. Now we know that when x is 0 positive, it lies between 0 and 1, and if x lies between 0 and 1, then fractional part of x is simply x. So it will be this limit x tends to 0 positive log e to the power x square plus 2 times under root x upon 10 under root x. Now if we put x as 0, this is log 1 is 0, and 10 0 is 0, so it is 0 upon 0 form, and when it is 0 upon 0 form, we can use L'Hopital's rule. Now if we apply L'Hopital's rule here, we can write this as limit x tends to 0 positive. Now this is 1 upon e to the power x square plus 2 root x into this is e to the power x square into 2x plus 1 upon under root x, and here it will be this secant square under root x 1 upon 2 root x. Now we'll write this as limit x tends to 0 positive 1 upon e to the power x square plus 2 root x, and here this value will be 2 x to the power 3 by 2 into e to the power x square plus 1, and here it will be secant square under root x, and then this under root x will cancel, and we'll take this 2 in the numerator. Now if you put x as 0, it will be this 2 into 1, and here will be this 1 into 1. So this value is 2. So for this function, left hand limit is log 2 and right hand limit is 2. So it has a non-removable discontinuity. So you'll have an irremovable discontinuity at x equals to 0, and that's your option D. Now here the question is, we are given three functions fx, gx and hx, and we have to find which of the following is or are true. Now A and B is hx is continuous or discontinuous at x equals 0. Now if we look at left hand limit at 0, it will be h 0 negative limit x tends to 0 negative, and when x is less than 0, it will be 1 by root 2, and then f of gx, and f of gx will be under root of 1 plus cos 2x minus under root of 1 minus cos 2x upon greatest integer function of cos 2x. Now this is limit x tends to 0 negative 1 by root 2. Now this is 2 cos square theta minus 1, so it will be this root 2 and then mod cos x and then minus, and this is root 2 mod sin x upon fractional part of cos 2x. Now we know that when x is less than 0, cos 2x will lie between 0 and 1, and if cos 2x lies between 0 and 1, fractional part of cos 2x will be simply cos 2x. Now first we'll check its form. So if we put x as 0, it will be this root 2 upon root 2, which is 1. So left hand limit of this function hx, it is 1, and if we find its right hand limit h0 positive, will be this limit x tends to 0 positive, and it is fx. Fx is 1 plus x minus under root of 1 minus x upon fractional part of x. Now when x is 0 positive, fractional part of x is simply x. So it will be this limit x tends to 0 positive under root of 1 plus x minus under root of 1 minus x upon x. Now if we rationalize this, we can write this as limit x tends to 0 2x upon x into under root of 1 plus x plus under root of 1 minus x. Now x and x will cancel, so this value will be 1. h0, it is given as 1. So left limit is equal to right limit is equal to function value. That means hx is continuous at x equals 0. Now it says f of gx is an even function. Now if we look at this gx is defined only on the left neighborhood of 0. So we cannot ascertain f of gx, it is an even function, because it is not defined on the right hand side of 0. So this option C is incorrect, and fx is an even function. Now if we find f minus x will be 1 minus x minus under root of 1 plus x upon fractional part of minus x. Now it will be equal to minus under root of 1 plus x minus under root of 1 minus x, and fractional part of minus x is 1 minus fractional part of x when x is not an integer. In the domain of fx, we do not have integers, but this is clearly not equal to fx or f minus x. So this function fx, it is not an even or odd function. That means this option D is also incorrect. So the only correct option is this option A. Now here the question is, we are given that f0 is 0 and f dash 0 is 1. For some positive integer case, show that this limit x tends to 0 1 by x fx by 2 f x by k, it is equal to 1 plus 1 by 2 plus 1 by 3 up to 1 by k. Now we can write this as limit x tends to 0 and then this summation f x by r, where r varies from 1 to k upon x. Now first we'll check its form. Now we put x as 0, it will be f0, and f0 is 0 and x, it is 0. So this is 0 upon 0 form, and if it is 0 upon 0 form, we can use L'Hopital's rule. So we can write this as limit x tends to 0, and then this summation r varies from 1 to k, and it will be this f dash x by r into 1 by r upon 1. Now this is summation r varies from 1 to k. This is f dash 0 upon r. Now f dash 0 is 1. So it will be this summation r varies from 1 to k, 1 by r, which is nothing but 1 plus 1 by 2 up to 1 by k. And this is what we need to prove in this question. Now here we have two questions. This first question is, we're given this function fx, which is x into e to the power of greatest near function of x plus mod x minus 2 upon greatest function of x plus mod x when x is unequal to 0, and we are given that f0 is minus 1. Now we need to check differentiability of this function at x equals 0. Now for differentiability, we'll first need to check its continuity. So we'll find its left hand limit, which is f0 negative, and it'll be this limit x tends to 0 negative x into e to the power of greatest real function of x plus mod x minus 2 upon greatest real function of x plus mod x. We let x as 0 minus h. So it will be this limit h tends to 0 positive. Now this is minus h, and it will be e to the power greatest function of minus h plus mod of minus h is h minus 2 upon greatest function of minus h plus mod of minus h is plus h. So it will be this limit h tends to 0 positive minus h into, now greatest function of minus h is minus 1. So it will be e to the power minus 1 plus h minus 2 upon minus 1 plus h. Now we put this limit, it is equal to 0. So f0 negative is 0, and we are given that f0 is equal to minus 1. That means this function fx, it is discontinuous at x equal to 0. And discontinuity, it implies non-differentiability. So this function is non-differentiable at x equal to 0. Now if we look at the second question, which is, we are given this function fx, and fx is defined as mod of 2x minus 3 into greatest net function of x if x is greater than or equal to 1, and it is sine pi x by 2 when x is less than 1. Now we need to discuss continuity and differentiability of fx in the interval 0 to 2. Now what we'll do is, we'll write this fx as sine pi x by 2 when x lies between 0 and 1. Now when x lies between 1 and 2, in that case greater function of x is 1. So it will be this mod of 2x minus 3, and when x is 2, this value will be 2 into 1, which is 2. Now we'll draw the graph of fx. This is 0, 1 and 2. Now first we'll draw the graph of sine pi by 2x. Now for sine pi by 2x, what we need to do is, we just have to draw the graph of sine x. So it is 0, this is pi, this is 2 pi, and we have to divide everything with pi by 2. So we divide everything with pi by 2. This point is 2, this is 4, and here it is 1. So from 0 to 1 will be this graph. Now when x is 1, this mod of 2x minus 3 will be 1. At 3 by 2 will be 0, and at 2 will again be 1. At 2 it is 2, so at 2 this value is 2. Now this function is discontinuous at x equal to 2. So in this interval from 0 to 2, there is only one point x equals to 2 where this function is not continuous, and this function is not differentiable at 1, 3 by 2 and 2. So it is not differentiable at x equals 1, 3 by 2 and 2. And that is the answer to this question. In this video, we'll study how to find composite function from piecewise defined functions. Now basically there are two methods. One of them is graphical method and the second one is algebraic method. So we'll study these two methods with 3 graded examples. Now this first example is, we are given this function fx, which is defined as minus 1 plus mod of x minus 1 when x lies between minus 1 and 3. Now clearly fx, it is a continuous function, and we have this mod x minus 1. Now root of x minus 1 is 1, rightmost plus, this is minus. So when x is less than 1, it takes a negative value, and when x is greater than 1, it takes a positive value. So we can write this function fx as, now for this first interval, when x lies between minus 1 and 1, we have this minus sign here, so it will be minus 1 and then minus x minus 1, and then we have the second interval where x lies between 1 and 3, so it will be this minus 1 plus x minus 1. So basically this function fx is defined as minus x when x lies between minus 1 and 1, and it is x minus 2 when x lies between 1 and 3. Now we look at our function gx. Now gx is defined as 2 minus mod of x plus 1 when the value of x lies between minus 2 and plus 2. X plus 1 has a critical point at minus 1. This is plus and this is minus. So now we can write this function gx as, now first we have this interval when x lies between minus 2 minus 1. Now it is 2, and then in this interval this is negative, so minus minus plus, so it will be this 2 plus x plus 1, and then we have from minus 1 to 2. Now here it will be positive, so it will be 2 minus x plus 1. Now gx is basically x plus 3 when x lies between minus 2 and minus 1, and it will be 1 minus x when x lies between minus 1 and 2. Now we need to find f of gx and g of fx. Now first we will find f of gx using graphical method. So we are going to use graphical method and we wish to find f of gx. Now basically f of gx is f and then gx. So essentially values of x will go into this function g, and then value of gx will go into this function fx. Now in this graphical method, what we do is, first step is we'll draw the graph of gx. Now gx is x minus 3 when x lies between minus 2 and minus 1. So between minus 2 and minus 1, this is x minus 3. Now we put x as minus 2, this value is 1. And if we put x as minus 1, this value is 2. So this is a straight line. So this function is x plus 3. Now for this next part, it is also a linear function. So at minus 1, this value is 2. And at 2, this value is minus 1. And at 0, this is 1. So this is 2, then 1, then 0, and then minus 1. And here this definition is 1 minus x. Now there is a definition change at -1. So we'll highlight this -1. So first step is draw the graph of gx. Now this graph is defined between -2 and +2, and there is a definition change at -1. Now the next step is draw horizontal lines at boundaries of definitions of fx. Now boundaries of definitions of fx are at -1, 1 and at 3. So what we'll do is we'll draw a horizontal line at -1. So we'll draw this horizontal line at -1. We'll draw a horizontal line at 1. And we'll draw a horizontal line at 3. And in addition to it, we'll write definition of fx. Now, when x lies between -1 and +1, definition of fx is -x. So we'll write -x in between these two lines. And when x lies between 1 and 3, this definition is x -2. Now, we'll mark all those points where these lines, they're going to intersect the graph of gx. Now, they're intersecting at this point, and at this point, and at this point. So we have already marked this point. Now this is x equals 0, and this point is x equals 2. So now we'll start writing the definition of f of gx. Now first definition is between -2 and -1. So when x lies between -2 and -1. Now in this case, since both the functions fx and gx, they are continuous, we need not bother about this equality sign. We can take it with this definition, or we can also take it with the next definition. Now in this interval, definition of gx is x plus 3, and this definition will go into this x minus 2. So it will be this x plus 3 minus 2. Now this next interval is between -1 and 0. So it will be this -1 x and 0. And in this case, definition is 1 minus x. Now this 1 minus x, it still lies in this interval. So here 1 minus x will again go to this x minus 2. So it will be this 1 minus x minus 2. And then we have this third definition when x lies between 0 and 2. And in this case, definition is 1 minus x. But here graph lies in between these two lines. So here this definition will go to minus x. So it will be this minus and 1 minus x. So basically f of gx will be x plus 1 when x lies between -2 and -1. It will be minus x minus 1 when x lies between -1 and 0, and it will be x minus 1 when x lies between 0 and 2. So this is our graphical method. Now we'll come to algebraic method. Now before algebraic method, we'll write fx and gx again. Now fx is minus x when x lies between -1 and 1, and it is x minus 2 when x lies between 1 and 3, and gx is x plus 3 when x lies between -2 and -1, and it is 1 minus x when x lies between -1 and 2. Now again we'll find f of gx. So we'll write f of gx. Now in this definition we'll replace x with gx. So it will be this minus gx when gx lies between -1 and 1, and will be gx minus 2 when gx lies between 1 and 3. So for this f of gx, we have defined everything in terms of gx. Now this gx itself has two definitions, x plus 3 and 1 minus x. So what we'll do is, now we'll expand it in 4 parts using definition of gx. Now first we'll use this definition, x plus 3. So it'll be this minus, and then gx is x plus 3, and then we'll write minus 1 when gx is x plus 3 less than 1. Now here we have to use AND, because this condition, it must be satisfied for these values of x. So together with this condition, we have to take into consideration domain of x also. So it will be this minus 2 x and then minus 1. Now we'll put this x plus 3 in this second definition. So it will be this x plus 3 minus 2 and then 1, and then it will be this x plus 3 less than equal to 3, and again where x lies between minus 2 minus 1. Now next definition is 1 minus x. Now we'll put 1 minus x in this first one. So it will be minus 1 minus x and then minus 1 minus x is less than 1, and here the condition is the value of x must lie between minus 1 and 2, and then this definition will go into the second part. So it will be this 1 minus x minus 2 when 1 is less than 1 minus x is less than equal to 3, and minus 1 is less than x is less than equal to 2. Now in this, what we'll do is we'll first solve these intervals. Now this is a minus 4 is less than equal to x, and this is less than minus 2, and here it is x lies between minus 2 and minus 1. Now there is nothing common in between these two conditions, so here there is no intersection of values of x possible. So this definition, it is not possible. Now if we look at this, now if we take this 3, then it will be this minus 2, and then x will be this 0, and here it is minus 2 x and minus 1. So in this case, we have this common interval between minus 2 and minus 1. So now we write this f of gx, and the first interval where it is defined as between minus 2 and minus 1, and here this definition is simply x plus 1. Now we'll solve this. Now if we subtract 1, it will be this minus 2 less than equal to minus x less than 0, and if we take this minus sign, then it is between 0 to 2, and here it is between minus 1 to 2. So the common interval between these two is value of x lies between 0 to 2. Now here this definition is x minus 1, and finally here it is 0 and then minus x and then 2. So between minus 2 and 0, and here it is from minus 1 to 2. So if we take intersection of these two intervals, it will be between minus 1 and 0, and here this definition is minus x minus 1. So that is the definition of f of gx using algebraic method. Now once we have this definition of f of gx, we can draw its graph. Now when x is minus 2, this value is minus 1. When x is minus 1, this value is 0. So this is x plus 1. Now when x is minus 1, this is 0. And when x is 0, this is minus 1. So this is minus x minus 1. And here, if we take x as 0, it is minus 1. And at 2, this value is 1. So that is the graph of f of gx. Now clearly, this function is continuous in minus 2 to 2, and it is not differentiable at these 2 points where we have these corners. So not differentiable at x equals -1 and x equals 0. So this is how we can write composite functions from the two given functions fx and gx. Now we'll draw the graph of g of fx. And here I'm just going to use graphical method. Now for g of fx, it is g of fx. That means value of x will go into f and value of fx will go into g. So here we'll have to draw the graph of fx. So first we'll draw the graph of fx. Now this fx is minus x between -1 and +1. So at -1 it is 1 and at +1 this is -1. So that's the definition of fx between -1 and +1. So this is your minus x, and then at 1 this value is -1, at 2 it is 0, and at 3 this is 1. So that's the definition, x minus 2. Now there is a definition change at 1. So definition changes at 1, and then boundary values are -1 and 3. Now we'll draw horizontal lines at boundary conditions of gx. So we'll draw a horizontal line at -2. So it'll be this -2. And then at -1. And then we'll draw a line at 2. Now when x lies between -2 and -1, definition is x plus 3. So here we'll have x plus 3. And here when x lies between -1 and 2, it is the one minus x. Now it intersects only at one point, and this point is already marked. So here we just have two definitions. So if we write g of fx, now this first interval is from -1 to 1. So when x lies between -1 and 1, definition is minus x, and it will go into this 1 minus x. So it will be this 1 plus x. And then next interval is from 1 to 3. So when x lies between 1 and 3, here the definition is x minus 2, and it'll still go to 1 minus x. So it will be 1 minus x minus 2. So this function will be 1 plus x when x lies between -1 and 1, and it will be 3 minus x when x lies between 1 and 3. Now we'll draw the graph of g of fx. Now for g of fx, when x is -1, this is 0, and when x is 1, this is 2. So it is this line 1 plus x, and when x is 1 it is 2, and when x is 3 it is 0. So that's the definition, 3 minus x. Now this g of fx, it is continuous in -1 to 3, and it is not differentiable at x equals 1. So this function, it is not differentiable at this point, x equals 1. So we can solve these composite functions either using graph or using this algebraic method. Now we'll take up the second example. Now we'll take this third case where we're given this fx and gx, and we need to find g of fx. Now first we'll use graphical method. We'll draw the graph of fx. Now when x is 0, this is 1, and when x is -1, this is 0. So that is the definition of fx, and since 0 is not included, it will be this open interval. And then when x is greater than or equal to 0, this is x square. So it is x square when x is greater than or equal to 0. So in this case, this fx, it has this discontinuity at 0. Here, there is a definition change at 0. Now we'll draw horizontal lines at -1 and 1. So we'll draw horizontal lines at -1 and also at +1. +1. Now we'll find their point of intersection. So we have this just one point of intersection here. We have another point of intersection which is given by this value. Now this point is graph of x plus 1 intersecting this line -1. So x plus 1 equals -1. So this point is -2. So basically this point is x plus 1 equals -1. And we also have another point of intersection, and this point is this graph of x square intersected by pi equals 1. So if x square equals 1, this point is also 1. So here we have three critical points, -2, 0 and 1. Now when x lies between -1 and +1, definition of gx is 2x, and when x is greater than or equal to 1, this definition is 3 minus x. Now we'll start writing g of fx. Now this first interval is x lies between -2 and not included 0. Here this definition is x plus 1, and we'll go to this definition which is 2x. So it will be this simply 2x plus 1. Now here, since this function is discontinuous at 0, we do not know whether we have to include 0 here or we have to include 0 in the next one. So what we'll do is, as of now, we won't bother about this equality sign. Now we'll find definition between 0 and 1. So when x lies between 0 and 1, here this definition is x square, and still between these two lines. So we'll go to this definition 2x. So it'll be this 2x square, and finally it'll be this x greater than 1. In this we have x square, and now I'll go to this 3 minus x. So it'll be this 3 minus x square. So that is the definition of g of fx. Now we have a problem with equality signs. So what we'll do is we'll find g of f0. Now f0 is when x is 0, f0 is 0. So it'll be this g0, and g0 is 2 into 0, 0. So we have to include this equality sign at a point where definition of g of fx is 0. So if we put 0 here, it will be 2. And if we put 0 here, it will be this 2x square. So we have to include this 0 here. And in the same way, we'll find g of f1. Now f1, it will be 1. So it will be this g1, and g1 is this 3 minus x, which is 2. Now if we put 1 here, it is 2. If we put 1 here, it is 2. Now since it is continuous at 1, we can put this equality sign anywhere. So that is the definition of g of fx. Now we'll solve this using algebraic method. So here we have to find g of fx, which is 2fx when fx lies between -1 and +1, and it will be 3 minus fx when fx is greater than or equal to 1. Now fx has two definitions. So first we'll consider this definition. So now we write this as 2 and then x plus 1 when x plus 1 lies between -1 and 1, and the condition with that definition is x is less than 0. And here will be this 3 minus x plus 1 when x plus 1 is greater than or equal to 1, and here the condition is x is less than 0. Now next definition is x square, so it will be this 2x square when x square lies between -1 and 1, and x is greater than or equal to 0, and then it will be this 3 minus x square when x square is greater than or equal to 1, and x is greater than or equal to 0. Now we'll solve these conditions. Now this is minus 2 less than equal to x less than 0, and this is x is less than 0. So intersection of these two conditions is this interval. So g of fx will be (2x plus 1) when x lies between minus 2 and 0. Now if you look at the second condition, here the condition is x is greater than or equal to 0, and here x is less than 0. Now there is nothing common between the two intervals, so this is not possible. Now if you look at this third one, x square is always greater than minus 1, and x square less than 1 is x lies between minus 1 and plus 1, and here x is greater than equal to 0. So intersection is x is greater than equal to 0 but less than 1. In this case, this definition is 2x square. And this third one is x square is greater than 1. That means x is greater than equal to 1, and x is greater than equal to 0. That means x is greater than or equal to 1. Then this definition is 3 minus x square. So this is the definition of g of fx using algebraic method. So this is how we find composite functions from two piecewise defined functions. Now here the question is, we are given this function fx, which is defined as x sine 1 by x sine 1 upon x sine 1 by x if x is unequal to 0 and x is unequal to 1 upon r pi. And it is also given that f0 equals f 1 upon r pi, and it is equal to 0. Now we need to check its continuity in the interval 0 to 1. Now the points where this function could be discontinuous is at x equals to 0, because we have this 1 by x, and also at the points where sine 1 by x is 0, because then again it will be 1 upon 0. So here we get 1 upon x equals r pi, or x is equal to 1 upon r pi. So we have to check for continuity at 0 and at 1 upon r pi. So first we'll check its continuity at x equal to 0. Now if we find this limit x tends to 0 fx will be this limit x tends to 0, and this is x sine 1 by x into sine 1 upon x sine 1 by x. Now first we'll check its form. Now this is 0 into, now this is sine infinite, and sine infinite is oscillating value between minus 1 and plus 1. And then here this is sine. Now this is 1 upon 0 and oscillating value. So here it will be this oscillating value from minus infinite to plus infinite, and value of sine will always lie between minus 1 and plus 1. So this is 0 into something finite, and 0 into anything finite is simply 0. And it is given that f0 is equal to 0. It means that this function fx, it is continuous at x equals 0. Now if we look at x equals 1 upon r pi, then we are going to write this limit as limit x tends to 1 upon r pi fx, and there will be this limit x tends to 0 x sine 1 by x into sine 1 upon x sine 1 by x, and this is 1 upon r pi. Now again we'll put the value. So this is 1 upon r pi into, now this is sine r pi, and sine r pi it is 0 into, and this value will be 1 upon r pi upon 0, and there will be sine infinite, and sine infinite is oscillating value between minus 1 and plus 1. Now 0 into something finite is 0. So this limit is 0, and we are given that f 1 upon r pi, it is also 0. That means this fx is continuous at x equals 1 upon r pi. So if it is continuous at 0 and if it is continuous at all 1 upon r pi, that means this function fx, it is continuous in 0 to 1. So this fx is continuous in this interval 0 to 1. Now we need to check its differentiability at x equals 0. Now for its differentiability, if we check its derivative, it will be this limit h tends to 0, and suppose we'll find its right hand derivative. It will be this h sine 1 by h into sine 1 upon h sine 1 by h minus 0 upon h. Now this h and h, it will cancel. Now we'll put this limit. Now sine infinite is oscillating value between -1 and +1, and here also this is sine infinite, which again is oscillating -1 to +1. So this f dash 0, it's an oscillating value, and if it is an oscillating value, this limit, it does not exist. That means fx is not differentiable at x equals 0. And that is the answer to this question. Now here the question is, we are given this function fx, which is x square mod cos pi upon 2x if x is unequal to 0 and it is 0 at x equals to 0. That means f0 is 0. Now first is show that f dash 0 exists and find its value. Now clearly this function is continuous at 0, because if we look at f0, it is 0, and f0 positive and f0 negative, it will be this 0 into and then cos infinite, and cos infinite is oscillating, and since there is this mod sign, it will oscillate between 0 and 1, and 0 into anything finite is 0. So value of left hand limit and right hand limit, it is also 0. That means fx is continuous at x equals 0. Now we need to find f dash 0. So first we'll find its left hand derivative. Now left hand derivative will be f dash 0 negative, will be this limit h tends to 0 h square mod cos pi upon 2h upon minus h. Now this h will cancel once. Now this is again 0 into cos infinite, and it will be 0. And if we check its right hand derivative, it will be f dash 0 positive, which is limit h tends to 0, and this is h square cos pi upon 2h upon h. Now this h and h will cancel, so which again is 0 into oscillating value 0 to 1, which is 0. So f dash 0 exists and its value is 0. That's your A part. Now in the B part it says, show that f dash 1 by 3 does not exist. Now if we look at the second part, that is, we need to check its differentiability at 1 by 3. So now we look at 1 by 3 negative. Now it will be this limit h tends to 0, and here will be 1 by 3 minus h whole square into mod cos pi, and this is 2 into 1 by 3 minus h minus, now f1 by 3, if we look at f1 by 3, f1 by 3 will be x square, which is 1 by 9 into mod cos 3 pi by 2, and mod cos 3 pi by 2 is 0. So this is 0 divided by minus h. Now what we'll do is we'll write this as limit h tends to 0. We don't have a problem with this expression because this is finite. So this is 1 by 9, and we'll take this 1 upon 3 out. So we can write this as cos 3 pi by 2, and this is 1 minus 3h mod minus h. Now we'll write this as limit h tends to 0, 1 by 9 mod cos 3 pi by 2, and we'll use binomial expansion of 1 minus 3h to the power minus 1 whole divided by minus h. Now this is limit h tends to 0, 1 by 9, and this is mod cos 3 pi by 2, and then this is 1 plus 3h and higher powers upon minus h. Now cos 3 pi by 2 plus theta is sin theta, so it will be this limit h tends to 0, 1 by 9 and sin 9 pi h by 2 and higher powers upon minus h. Now, so basically f dash 1 by 3 negative is minus pi by 2. Now we look at its right hand derivative. So it will be this 3 plus 1 by 3 plus h, 1 by 3 plus h. Here also will be this plus h, 1 by 3 plus h, this is plus. Now here will be this minus 1 minus 3h, and here will be this plus, and then cos 3 pi by 2 minus theta is minus sin theta. So there will be this minus sign, but then we have this mod, so it won't make a difference. So it will be this plus sign. So in that case, the value of this limit will be pi by 2. So it's the right hand derivative at 1 by 3. It is plus pi by 2, and since left hand derivative is not equal to its right hand derivative, that means f dash 1 by 3 does not exist. Now in the third part it says, for what values of x, f dash x fail to exist. Now since we have this mod function, and we know that this mod, it is not defined when fx is 0. So this function, it won't be defined for all the points where cos pi by 2x, it is equal to 0. Now cos is 0 at odd multiple of pi by 2. So clearly we get this x as 1 upon 2n plus 1. So for this function, f dash x fail to exist at all point where x is 1 upon 2n plus 1, where n belongs to an integer. Now here we have 4 questions. 1, 2, 3 and 4. Now we'll start with this first one, and it says, let fx be defined on minus a2 plus a with a greater than 0, and assume that f is continuous at x equals to 0. That means f 0 minus h is equal to f 0 plus h, and it will be equal to f0. It is given that limit x tends to 0, fx minus f kx upon x, it is equal to alpha, where k lies between 0 and 1. Then compute f dash 0 positive and f dash 0 negative, and comment on differentiability of f at x equals 0. Now what we'll do is, we'll first solve this limit. Now if we take its left hand limit, it will be this limit h tends to 0, and this is f minus h minus f k into minus h upon minus h, and this value will be alpha. Now what we'll do is, we'll subtract f0 and we'll add f0. Now we can write this as this limit h tends to 0. Now this is f minus h minus f0 upon minus h, and then if we take this minus common, it will be this limit h tends to 0, f minus kh minus f0 upon minus h, and this is equal to alpha. Now this is nothing but, this is left hand derivative at 0, so it will be this f dash 0 negative, and here if we multiply and divide it with k, now this again is 0 minus kh minus f0 upon minus kh, so it will be left hand derivative at 0. So this is k into f dash 0 negative, that is equal to alpha. So from here we can say value of f dash 0 negative is alpha upon 1 minus k. Then the same way we'll find its right hand limit. Now for this right hand limit, we can write limit h tends to 0 fh minus fkh upon h. Now we'll subtract f0 and add f0, and this is equal to alpha. So it will be this limit h tends to 0 fh minus f0 upon h minus this limit h tends to 0 fkh minus f0 upon h, that is equal to alpha. Now here again we'll multiply and divide it with k. Now these are right hand derivative at 0. So it will be f dash 0 positive minus k into f dash 0 positive, that is equal to alpha. So value of f dash 0 positive will be alpha upon 1 minus k. And since they are equal, f dash 0 exists and the value of f dash 0 will be alpha upon 1 minus k. And therefore this function is differentiable at x equals 0. Now the second question is, we are given this function f from r to r defined by this equation fx plus y equals fx into fy, and it says function is differentiable at x equals to 0 and f dash 0 is 2. Now show that f dash x equals 2fx for all x belongs to r, and hence determine fx. Now what we'll do is we'll find the value of f0, and for that we'll put both x and y as 0. Then we can write this as f0 equals f0 square. So from here we get two conditions, that either f0 is 0 or f0 is 1. But in this equation, if we put y as 0, we get fx equals fx into f0, and if f0 is 0, then this function fx will be a constant function, and then this f dash 0, it cannot be 2. So we'll discard this possibility that f0 is 0. So from here we can say value of f0 is 1. Now we'll find f dash x. Now f dash x is defined as this limit h tends to 0 f x plus h minus fx upon h. Now we know fx plus h will be fx into fh. So we can write this as this limit h tends to 0 fx into fh minus fx upon h. Now we'll take this fx common and we'll take it, or this limit. So it will be this limit h tends to 0 fh minus 1 upon h. Now we can also write this as fx and then this limit h tends to 0. Now this is fh minus, and we can write this one as f0. So it will be fh minus f0 upon h, which is nothing but f dash 0. So we can write this f dash x as fx into f dash 0, and f dash 0 is 2. So from here we can say this f dash x will be 2 times fx, and this is what we need to prove. Now we need to find fx also. So what we'll do is we'll use differential equation. We can write this as f dash x upon fx will be equal to 2, and we integrate, we can write log fx and it will be equal to 2x plus c, or fx will be e to the power 2x into e to the power c, and e to the power c is some constant. Now we know that when x is 0, fx is 1. So if we put x as 0 and fx is 1, then value of e to the power c is 1. So from here we can say our function fx is e to the power 2x. And that is what we need to find in this question. Now this third question is, let fx be a real valued function not identically 0, satisfying the equation f x plus y to the power n, it is equal to fx plus f y to the power n, where n is an odd natural number and it is true for all real xy, and f dash 0 is greater than or equal to 0. Now we need to find the value of f10. Now first we'll find the value of f0. Now if we put x and y both 0, it will be this f0, this is f0, and this is f0 to the power n. So from here we can say value of f0 is 0. Now we write f dash x. Now f dash x will be this limit h tends to 0 f x plus h minus fx upon h. Now we write this h as this limit h tends to 0 f x plus h to the power 1 by n to the power n minus fx upon h. Now we know that fx plus y to the power n is fx plus fy to the power n. So we can write this as this limit h tends to 0, and will be this fx plus fy, which is fh to the power 1 by n whole to the power n minus fx divided by h. Now this fx and fx will cancel. Now if we put x as 0, we can write f y to the power n is fy whole to the power n. That means we can take this power out of this function, or we can put this power inside this function. So if we put this power inside this function, we can write this as this limit h tends to 0 f h upon h. Now f0 is 0, so we'll write this as fh minus f0 upon 0, and this is nothing but this is f dash 0. Now let f dash 0 is some constant, say a. So now we have f dash x equals a. Now we integrate, we can write fx equals ax plus c. Now when x is 0, f is 0, so clearly value of c is 0. Now we need to find one more value to find the value of a. So we'll again go back to the equation. So if we put x as 0 and y as 1, we can write f1 and will be equal to f0, which is 0, plus f1 to the power n. So from here we'll get either f1 is 0 or f1 is 1. Then in that case, this fx will be 0 throughout constant, but it is given that it is not identically 0. That means value of f1 is to be taken as 1. So if we put x as 1, fx is 1. So value of a is 1. So in this case, fx is simply x. We need to find the value of f10. Value of f10 is 10. Now this fourth question is, we are given this function f, and it says if this function is differentiable at 0, then show that it is differentiable for all x belongs to R. Now if it is differentiable at 0, that means f dash 0 negative must be equal to f dash 0 positive. And we'll take this as sum f dash 0. Now we need to show that this function is differentiable for all x. Now what we'll do is we'll find f dash x. Now f dash x will be this limit x tends to 0, and this is f x plus h minus fx upon h. Now in this equation, what we'll do is we'll take x as 3x and y as 3h. Then we can write f x plus h will be f3x plus f3h plus f0 upon 3. And the same way we put x as 3x and y as 0, we can write fx as f3x plus 2f0 upon 3. So now we can write this f dash x as this limit x tends to 0 f3x plus f3h plus f0 minus f3x minus 2f0 whole divided by 3h. Now f3x will cancel, so we can write this as this limit x tends to 0, and this is f3h minus f0 upon 3h, which is nothing but f dash 0, which is some constant, say a. Now this fx, it is ax plus b. So this function, if it is differentiable at 0, it is differentiable for all x belongs to R. Now the question is, we are given this function fx. Now we need to check its continuity and differentiability at x equals 0. Now when x is unequal to 0, we are given this function fx as this log basis a, and this is a mod of greatest new function of x plus greatest function of minus x, this mod whole to the power x into, and here will be this a to the power 2 upon greatest integral function of x plus greatest function of minus x by mod x minus 5 upon 3 plus a to the power 1 upon mod x when mod of x is unequal to 0 and a is greater than 1. Now what we'll do is, we'll take this limit x tends to 0 fx. Now we know that when x approaches 0, it is not exactly equal to 0. That means it is not an integer. And if x is not an integer, then greater function of x plus greatest new function of minus x, it is nothing but minus 1. So we'll simplify this a bit. We'll write this as this limit x tends to 0, and it will be this log a, and will be this a to the power x, and here it will be this minus 1, so a to the power minus 2 mod x minus 5, and it will be this 3 plus a to the power 1 upon mod x. Now log a base a is 1, so it will be this limit x tends to 0 x into a to the power minus 2 mod x minus 5 upon 3 plus a to the power 1 upon mod x. So, and that is the definition of this function in the neighborhood of x equal to 0. So we'll use this definition for all of the parts. Now we calculate this limit. This is 0. Now a to the power 0 is 1 and 1 minus 5 is 4. And here this value will be 3 plus a to the power infinite is infinite and 0 upon infinity is 0. And we are given that f0 is 0. That means this function fx, it is continuous at x equals 0. And as we have this x here which is 0, we have not taken left hand limit and right hand limit separately. We could have done that, but then we would have ended up getting the same answer. Now we need to check its differentiability at x equals 0. Now if we check its left hand derivative, it will be f dash 0 negative, which is given by this limit h tends to 0. Now f minus h, so it will be this minus h a to the power minus 2h minus 5 upon 3 plus a to the power 1 by h minus 0 upon minus h. Now this minus h and minus h will cancel. Now we put this limit, this is minus 4 upon a to the power infinite is infinite. So it will be 0. So left hand derivative at 0 is 0. In the same way, if we find its right hand derivative, will be this limit h tends to 0, h e to the power minus 2h minus 5 upon 3 plus e to the power 1 by h minus 0 upon h. Now h and h will cancel. So again this value will be 0. So in this case, this function is differentiable at 0, its value is 0. So answer to this question is, this function is continuous and differentiable at 0, and that's your option B. Now here the question is, we are given this function fx, which has this definition when x is equal to pi by 2 and f pi by 2 is 3. Then we need to find whether f is continuous or differentiable at pi by 2. Now we know that at pi by 2, value of sin x is 1, but at both pi by 2 negative and pi by 2 positive, sin x is less than 1. And if sin x is less than 1, then sin x will be greater than sin cube x. So for this function, in both left hand and right hand neighborhood of pi by 2, sin x is greater than sin cube x, and therefore mod of sin x minus sin cube x will be equal to sin x minus sin cube x. So we let this function fx in the neighborhood of x equal to pi by 2 as greatest in the function of 2 sin x minus sin cube x plus sin x minus sin cube x upon, and this is 2 sin x minus sin cube x, and then minus sin x plus sin cube x. Now this is 2 sin x plus sin x, so will be this 3 sin x. So it will be 3 sin x minus sin cube x, and here also we have sin x minus sin cube x. Now I'll cancel. So in the neighborhood of pi by 2, this function is 3. So f pi by 2 negative, it is equal to f pi by 2 positive, it is equal to f pi by 2, and it is 3. Basically it's a constant function, and if it is constant function in the neighborhood of pi by 2, it is both continuous and differentiable. So answer to this question is this option A. Now here the question is, we are given this function fx, which is 2x into under root of x cube minus 1 plus 5 under root of x into under root of 1 minus x to the power 4 plus 7x square into under root of x minus 1 plus 3x plus 2. And we need to find its continuity and differentiability at x equals 1. Now first we'll find domain of this function. Now since we have square root, this x cube minus 1, it should be greater than or equal to 0. That means x is greater than or equal to 1. Now for this we'll get x is greater than or equal to 0. Now for 1 minus x to the power 4, it should be greater than or equal to 0, or x to the power 4 minus 1 should be less than or equal to 0. We'll have minus 1 plus 1, and this is plus minus and plus. So we'll get x should lie between minus 1 and plus 1. Here x is greater than or equal to 1. Now if we take intersection of all these intervals, then this function is defined at only one point. So this function is defined only at x equals to 1, and the value of this function at 1 is, now this is 0, this is 0, this is 0, and 5. So basically this function, it is defined only at this point 1, and at this point its value is 5. So it is an isolated point. Now at 1 there is no neighborhood, neither on the left hand side nor on the right hand side. Now we have an isolated point, and then literature says at this point the function will be continuous but not differentiable. So the function is continuous but not differentiable at x equals to 1, and that's your option A. Now here the question is, we are given this function which is defined as fx plus y and is equal to fx plus fy plus mod xy plus xy square for all xy belongs to R, and it says f dash 0 is 0. Now if we put x and y as both 0, we'll get f0 as 0 as well. So at 0, fx is 0 and f dash x is 0. Now at 0, this function is continuous as f dash 0 exists. So we'll check its continuity at any general point. Now at x equal to a, its left hand limit will be f a negative, and there will be f a minus h. We can write this as f a plus f minus h plus mod a into minus h and a into h square. Now this is 0, and f minus h will be equal to f0, and that will be equal to 0. In the same way, f a plus h will again be equal to f a. So this function is continuous for all x belongs to R. Now we need to check its differentiability. Now we can write f dash x as this limit h tends to 0 f x plus h minus fx upon h. Now we can write this as this limit h tends to 0. Now fx plus h is fx plus fh plus mod x into h plus x into h square minus fx whole divided by h. Now this fx and fx will cancel, and f0 is 0. So we'll rearrange this as limit h tends to 0. We'll write this as fh minus f0 upon h plus, now here h and h will cancel, and here it is this xh. Now this is nothing but this is f dash 0. So we can write this as f dash x as f dash 0 plus mod x plus 0, and we are given that f dash 0 is 0. So basically f dash x is equal to mod x. Now since f dash x is continuous, this function is differentiable for all x belongs to R. So answer to this question is option B, f is differentiable for all x belongs to R. And in this question it says, let f be a differentiable function in the open interval AB, then which of the following statements must be true? The first one is f is continuous on closed interval AB. Now that's not true. Suppose we take this function fx as 1 by x in the interval 0 to 1. In open interval 0 to 1, this function is differentiable, but still it is not continuous at x equal to 0. So that means the statement 1 is not always true. And second one is f is bounded in the open interval AB. Now that's also not true. Same example shows this function, it extends up to infinite. So that means the statement 2 is also incorrect. Now it says, if there are 2 points A1 and B1 which lie between AB such that f A1 is less than 0 and f B1 is greater than 0, then from Bolzano's theorem we know that there exists a point C in the interval A1 comma B1 such that FC is 0. That means the statement 3 is correct. So the only statement correct in this case is this third, and that's your option D. Now the question is, we are given this function fx and it says if f is continuous at 0, then find the value of b. Now if we look at its right hand limit, it will be f0 positive, and it is limit h tends to 0 a plus sine 0 plus h upon h. Now greater function of sine h is 0. So it is not 0 upon 0 form, but it is 0 upon h, and 0 upon h is 0. So this is A. And as I've told you previously also, this get a function of x, it doesn't take a limiting value. It always takes an exact value. So get a function of x, it cannot approach a. It'll be exactly a. So in this case, right limit is a. And if we find its left hand limit, f0 negative, it'll be this limit. H tends to 0. This is b plus. Now this is sine minus h. So it'll be this minus sine h plus h upon, and then it'll be this minus h cube. So it'll be this minus h cube. Now we can write this as this limit h tends to 0, and this is b plus, and this is sine h minus h upon h cube. Now if we use the expansion of sine h, we can write this as this limit h tends to 0, this is b plus, and this is h minus h cube upon factorial 3 plus higher powers of h minus h upon h cube. Now this h and h will cancel, this h cube will also cancel, so this limit will be limit h tends to 0, b plus minus 1 by 6 plus higher powers of h. Now this value will be negative, so it will be less than 0, and get a function of 0 negative is minus 1, so it will be this b minus 1. Now if this function is continuous, then a must be equal to b minus 1, or the value of b is a plus 1, and that's your option B. And we can find the value of a and b also using this condition. Now here the question is, we are given this function fx, which is x when x is rational, and it is 1 minus x when x is irrational. Now it says find the continuity of f of fx. Now though it is not asked in this question, we'll discuss continuity of fx. Now literature says if we have any function fx which is defined as f1x when x is rational and f2x when x is irrational, then this function is continuous only at points where f1x equals f2x. So this function will be continuous for only those points which are solution of this equation f1x equals f2x. Now what is the reason for that? Now suppose we have this function which is defined differently for rationals and irrationals. Now at any point a, in the neighborhood of a, there will be infinitely many rationals and irrationals. So if we take its left hand limit, its left hand limit will be this oscillating value f1a, f2a, and on the right hand also it will be this oscillating value f1a and f2a. So both the limits on the left hand side and the right hand side, they'll be oscillating, and therefore this limit will not exist except for the cases when it is not oscillating, and not oscillate if both the values f1a and f2a, they are equal. So that means this function is continuous for only those values where f1x must be equal to f2x. Now for this function, if we equate them, x equals 1 minus x, we'll get value of x as 1 by 2. So fx is continuous only at 1 by 2, and at all the points this function will be a discontinuous function. Now for this question, we do not need any of this analysis. So in this, what we need to do is we need to find f of fx. Now when x is rational, fx is x, and therefore this fx will be a rational number, and if fx is rational, then f of fx will be simply x. Now when x is irrational, fx is 1 minus x, and 1 minus x is irrational, and if it is irrational, it will go to this 1 minus x, then in that case f of fx, it will be 1 minus x, which is x. So whether rational or irrational, this fx will always going to be x. That means it is continuous for all x belongs to 0 to 1, and that's your option A. Now for this question, we need to find jump of discontinuity. Now if we look at its left hand limit, will be f0 negative, and f0 negative is this limit x tends to 0 negative e to the power greatest new function of x minus e to the power fractional part of x upon e to the power x. Now we let x as 0 minus h, so it will be this limit h tends to 0 positive, and will be e to the power greatest net function of minus h minus e to the power fractional part of minus h upon e to the power of minus h. Now greater function of minus h is minus 1, so it will be this limit h tends to 0 positive, so it will be this e to the power minus 1 minus, and fractional part of minus h will be 1 minus h, so it will be e to the power 1 minus h upon e to the power of minus h. Now we'll put h equals 0, it will be this e to the power minus 1 minus e upon 1. So our left hand limit is 1 upon e minus e. Now we'll find its right hand limit. Now for right hand limit, we'll take limit h tends to 0 positive. Now we'll replace x with 0 plus h, so it will be this sine fractional part of h upon fractional part of 10h. Now when h is greater than 0 but less than 1, then fractional part of h is h, and also when h is positive, 10h is also 0 positive, so fractional part of 10h will also be 10h. So it will be simply this limit h tends to 0 sin h upon 10h, and which is 1. So once we have left hand limit and right limit, we can calculate jump of discontinuity, and jump of discontinuity is mod of 1 minus 1 by e minus e, which is 1 plus e minus 1 upon e, and that's your option B. Now here the question is, we are given this function gx and we have to find number of points of non-differentiability. So this gx is greatest new function of x square into fractional part of cos square 4x plus fractional part of x square into greatest new function of cos square 4x plus x square sin square 4x plus greatest function of x square into greatest new function of cos square 4x and plus fractional part of x square into fractional part of cos square 4x. Now what we'll do is, we'll take these two together. Now here we'll take get a function of x square common, and here this is fractional part plus greater function of x. Now we know that fractional part of x plus greater function of x is nothing but x, so it will be cos square 4x, and this will take fractional part of x square common. Now again this is greater function of x plus fraction part of x, so it will be cos square 4x plus x square into sin square 4x. Now here we'll take cos square 4x common. Now again this is fraction part of x plus greater function of x, so it will be this x square cos square 4x plus x square sin square 4x. Now we take x square common, this is sin square theta plus cos square theta. So essentially this gx is nothing but x square, which is continuous and differentiable. So number of points where this function is non-differentiable is simply 0, and that's your option D. Now we are given this function fx as x plus mod x into mod x, and we need to find which of the following is or are correct. So what we'll do is, we'll write this function piecewise. When x is less than 0, we know that mod x is minus x. So this function will be 0. And when x is greater than or equal to 0, mod x is plus x. So in that case, it will be simply 2x square. Now, f0 negative, it is 0. And f0 is equal to f0 positive, as we have this equality sign here, and it will be 0. So this function is continuous. Now, if we look at f dash x will be 0 when x is less than 0, and it will be 4x when x is greater than 0. Now, f dash 0 negative, it is 0, and f dash 0 positive is also 0. So we can take this equality sign. That means this f dash x is continuous. Now, if we look at f double dash x, it will be this 0 and 4 when x is less than 0 and x is greater than 0. So this f double dash x, it is not continuous, and f dash x is not differentiable at x equal to 0. So the only options correct are A and C. Now here we are given this function fx, which is greatest integer function of x when x lies between minus 2 and 0, and this is mod x when x lies between 0 and 2. Now we draw the graph of fx. Between minus 2 and minus 1, it will be minus 2. And between minus 1 and 0, it will be this minus 1. And when x is greater than 0, mod x is simply x. So it will be this x. So that is the graph of fx. Now we are given this hx, which is secant x in the interval minus 3 pi by 2 and 3 pi by 2, except all the points where it is not defined. Now if we look at graph of secant x, now this is pi by 2 minus pi by 2, this is 3 pi by 2, and this is minus 3 pi by 2. So this is 3 pi by 2 minus 3 pi by 2 minus pi by 2 and pi by 2. Now this is 1. So we have minus 1 and plus 1. And that's actually gx, not hx. Now first we'll find f of gx. So once we have gx, we look at definition of fx. Now critical points are minus 2, 0 and 2. So we'll draw a line at minus 2, 0 and plus 2. And we'll find these point of intersections. Now if we take secant x as 2, then cos x is 1 by 2. And if cos x is 1 by 2, this point is pi by 3. This point from minus pi by 3 to plus pi by 3. And secant x equals minus 2, cos x equals minus 1 by 2. So it will be this 2 pi by 3. And this is pi plus pi by 3 is 4 pi by 3. And here we will have minus 2 pi by 3 and minus 4 pi by 3. When x lies between minus 2 and minus 1, this definition is minus 2. In between these two, this definition is minus 1, and here this definition is x. So we can write f of gx as minus 2 when it lies in this interval, and x lies from minus 4 pi by 3 to minus 2 pi by 3, except at this point, which is minus pi, and from 2 pi by 3 to 4 pi by 3 except pi. So there's this definition is minus 2, and at x equals minus pi and plus pi, this value is minus 1, because these are the points where this value is minus 1. and then when x lies between minus pi by 3 to plus pi by 3, both included, this is x. So it will be this secant x. If we draw the graph of f of gx, it will be, now this is minus 4 pi by 3, and this is minus 2 pi by 3, and this is minus pi, this is minus pi by 3, this is plus pi by 3, this is 2 pi by 3, pi, and 4 pi by 3. Now in between minus 2 pi by 3 and 4 pi by 3, this value is minus 2, except at minus pi, where this is minus 1, and here also it is minus 2, except at pi, and in between minus pi by 3 and plus pi by 3, this is secant x. So it will be this value. Now the first question is, limit of f of g exists at which of the following point? Now at minus 1 will lie here. So at minus 1 it will exist. So this a, it matches with p. At pi, so here it is discontinuous, but still limit is going to exist. So this q. Now at 5 pi by 6, which is pi minus pi by 6, it is continuous at this point, so it will be this r. And then at minus pi also will be this s, and at pi by 3. At pi by 3 we have a defined left hand limit but a non-defined right hand limit, and if limit is defined only on one side, then too this limit is defined. So it will be p, q, r, s and t. And points of discontinuity of f of gx will be discontinuous at minus pi and plus pi. So it will be discontinuous at minus pi and plus pi. So this c, it matches with q and s. Now points of differentiability of f of gx. Now at minus 1 it will be differentiable. So for d we have p. At pi it is not differentiable. At 5 pi by 6 it will be differentiable. So it will be this pr. At minus pi it is not differentiable. At pi by 3 we just have to check its left hand derivative, and left hand derivative for this function will exist. So it will be this p, r and t. And then we have this g of fx. Now for g of fx, definition is only secant x, but here x should not be plus pi by 2. So this is one value missing, and this value will be at pi by 2. So g of fx will be secant minus 2 when x lies between minus 2 and minus 1. It will be the secant minus 1 when x lies between minus 1 and 0, and it will be secant x when x lies between 0 to 2 except pi by 2. Now this limit, it does not exist at minus 1 and all the points it is defined. So this b, it matches with p, and that is the answer to this question. Now here the question is, we are given this function fx which is defined as x plus 1 to x square minus 6x plus 6, and this gx which is defined from t minus 1 to t fx dx. Then which of the following statement is a true statement? Now fx is continuous and differentiable in 0 to 2. Now if we look at f1 negative, it will be this 1 plus 1 2, and f1 positive, and it is f1 will be plus 2. So this function is continuous at x equal to 1, and we have to take equality at only one point. So that will be only at the second definition. And we differentiate this f dash x will be 1 when x lies between 0 and 1, and it is 4x minus 6 when x lies between 1 and 2. Now f dash 1 negative is 1 and f dash 1 positive is minus 2. So it is continuous but not differentiable at x equal to 1. Now we have to find maxima and minima for this function. Now this function g, it is defined as gt, and it will be this t minus 1 to t fx dx when t belongs to 1 to 2. We find g dash t will be ft minus ft minus 1, where t lies between 1 and 2. If t lies between 1 and 2, this is ft in this interval. So it will be this 2t square minus 6t plus 6 minus, when it is t minus 1, it will lie between 0 and 1. And between 0 and 1, this is x plus 1. So this definition will be t minus 1 plus 1. Now this 1 and 1 will cancel. So it will be this 2t square minus 7t plus 6. Now this is 2t minus 3 into t minus 2. So we get two values, 3 by 2 and 2. This is plus, minus and plus. So there is a maxima at t equals 3 by 2 and there is a minima at t equals 2. So the only correct options are B and C. Now here the question is, fx is defined for x greater than minus 1. And it says, if f0 is 1 and f dash 0 is 0 and 1 plus fx into f double dash x, it is equal to 1 plus x, and if x is greater than 0, then f dash x is which of the following? Now if we look at f double dash x will be 1 plus x upon 1 plus fx. Now since this function has a continuous derivative and f double dash x exists, that means this 1 plus fx, it must not be equal to 0. So it will be either always positive or it will be always negative. That is given that at 0, this value is 1. So at 0, this value is positive. So that means this 1 plus fx, it will be greater than 0 for all x greater than 0. And this 1 plus x is also positive. That means f double dash x is greater than 0 whenever x is greater than 0. Now it implies that f dash x is an increasing function, and if x is greater than 0, then f dash x, it will be greater than f dash 0, as this function is increasing and the value of f dash 0 is 0. So from here we can say value of f dash x is always greater than 0. That means f dash x is always positive, and that's your option A. Now here we are given this function fx, which is defined as x square minus 2 mod x. Now gx is defined as minimum of fx in minus 2 to 0 and maximum of x from 0 to 3. Now we'll draw this graph, and for this we'll start with the graph of y equals x square minus 2x. Now graph for this function is, roots are 0 and 2 and this is 1, and at 1 this value is minus 1. Now we'll take the transformation of mod x. So it will be x square minus 2 mod x. So we'll erase the graph from second and third quadrant, and then we'll take the reflection of left on right. So this function, it will be drawn like this. Now this is 0, this is 2, this is minus 2, this is minus 1, and this is plus 1, and this value here is minus 1. Now it says when x lies between minus 2 and 0, gx is minimum of ft. Now between minus 2 and minus 1, since this function is decreasing, its minimum value will always occur at the end of the interval. So from minus 2 to minus 1, gx is simply fx. Now in between minus 1 and 0, minimum value will always be at minus 1, which is minus 1. So this is going to be the graph of gx when x lies between minus 2 and 0, and here 0 is not included. Now it says maximum of fx from 0 to 3. Now at 0 this value is 0, and here it is a decreasing function. Between 0 and 2, maximum value is going to be the value at 0. So from 0 to 2 it will be this straight line, and then from 2 to 3 this function increases, and that is it. So this blue graph is the graph of gx. Now at how many points gx is discontinuous in its domain? it is only at 1 point, and at how many points it is not differentiable? It is not differentiable at 0 and 2. So at 2 points, and that's your option C. So the correct options are B and C.